Hello everyone, Dr. Shane here. So this particular lesson will mark the end of the material for the first exam, probably. I think by now you realize I make these videos way in advance. In fact, almost all of them before the semester even started. But if we go by based on the last few years I've taught this course, that's kind of where we'll end. It'll be a nice way to stop. And there's an exam checklist on D2L as well. So we're going to sprint a little bit with this one because there's some stuff you simply don't need to copy down. Or you can just stop the video and write things down and then pick it up later. So we're going to kind of sprint a little bit here. So get warmed up and get ready to go. And the first thing is you do not have to copy any of this stuff down. Okay, there's a handout on D2L that gives you all of the information about the solutions, gives you the significant figures and everything, and goes on from there, even gives you the molecular structures. So you do not need to write any of this down. I just want to make a couple points here. Why did I make these solutions? So glucose is a solid dissolved in water. Glucose is polar. There's a bunch of OH bonds. You can have dipole-dipole interactions, more specifically, hydrogen bonding. Glucose also does not break apart or dissociate into smaller pieces when you put it in water. That's important. It's a covalent molecule. The second one is an ionic compound dissolving in water. This does dissociate into 3 particles, 1 cobalt plus 2 cation and 2 chlorine minus 1 anions. That's important down the road. The last one is a liquid dissolved in another liquid. So methanol dissolved in ethanol. How do you know which one is the major component? Well, that's the data. So that's why I chose these 3. And you do not need to write any of this down. So this is all data that we will use for future calculations. The only thing I want to point out here is significant figures. You're obviously given significant figures with masses in a volumetric flask. I wish I had props here at home with me, but volumetric flasks can often go to 2 decimal place precision. So we're going to have 5 significant figures with this volumetric flask, 4 significant figures with this volumetric flask, and 4 significant figures with this volumetric flask. Just to point that out. All right, let's motor. So this is topic number 4, properties of solutions, the basic definitions and concepts. And well, let's just get them all down. And I'll make some examples on the next slide. So you can stop the video if you want to. So just tells you what a solution is. It's the solute, the smaller substance, dissolved in a solvent, the greater substance, to form a homogeneous mixture. And that can actually be solids, liquids, and gases. Most of what we're going to do are going to be a solid dissolving in a liquid, and occasionally a liquid dissolving in a liquid. And concentration, we've done that before. Most common unit of concentration in chemistry is molarity. And then soluble, fine. If a solid dissolves in a liquid, it's soluble. If it's one liquid dissolving in another liquid, that's called miscible. The opposite there are insoluble. Okay. If something's insoluble, that means it remains as a solid, if it's a solid. And immiscible would be something like oil and water would be immiscible. I mean, you can write that down as an example if you want to. Always go to the book too. And then saturated means you've added the maximum amount of solute to a given amount of solvent. It won't dissolve anymore. It won't be more soluble or more miscible. I don't think there's too many examples I want to show you here. I do want to sneak in 2 units of concentration on you to make a point. Okay, concentration is, you have to pay attention to, are you doing per unit volume of solvent or per unit volume of the entire solution combined? That is a subtle difference. So just keep that in mind when we do this. Is it just the solvent or the total solution? All right. So 2 units of concentration that are pretty easy are mass percent and volume percent. So I'm just kind of sneaking these in on you so we can do more sophisticated ones later. Well, they're both percentages. So it's what percent of the solute is it of the entire solution. So mass percent is the mass of the solute over the mass of the solution times 100. Volume percent is exactly the same thing except using volumes. So that's going to get a little tight here. So the volume of the solute over the volume of the solution times 100. Now, it's important to know that not every unit of concentration, measure of concentration, is appropriate. So for the first one, mass percent, that would be totally appropriate for solution 1. Because everything's a mass. You're given mass of water, you're given a mass of glucose. Volume percent would not really be appropriate there because volume of a solid sample like glucose, that just doesn't make sense. So in this case, the methanol-ethanol solution would make sense. So solution number 3. So let's just jam in some numbers so we can get used to doing the calculations. Now keep in mind, this is the mass of the solution, the volume of the solution. So we have to add a couple things together. So for solution 1, the mass percent would be, just put in the numbers, we're going to take 15.58 grams of glucose. I really should label that 15.58 grams glucose, just to make that, but you can do that just to make this go a little faster, over 15.58 grams of glucose plus 249.52 grams of water times 100. And I think we're going to get 4 sig figs on this. So in this case, you will get 5.877% glucose by mass. All right, to try to get you involved a little bit more, go ahead and do the same thing, except use volumes for the methanol-ethanol solution 1. So, I mean, I'll do the math over here, but so kind of separate that out. So put in your number for solution number 3 over here, and you should come out with, I believe, to 3 sig figs, 3.00% by volume. And that's going to be, methanol, 3% by volume. And this one's pretty easy, so I think you're taking volume percent, in this case is going to be 1.50 milliliters of methanol, because that's a solvent. It's there in the smaller amount. I didn't write down a lot of examples there. So that's the solute. And you're just adding enough ethanol to get to a total volume. So we actually don't have to do any math here for this one, for the denominator. Total solution times 100. And you should get about 3%. Okay, so that's enough for the introduction. There's a bunch of stuff we probably really don't have to do very much at all. So again, we're sprinting through this initial part. Oh, don't even need that. Didn't even make any other slides. Water is pretty much our universal solvent. So when water is used, we're talking about aqueous solutions. And I think we already did all of this, either this semester or even last semester, but we're just blasting through this. So water, you already know some stuff. It's bent. It's polar. We know that. It's this. It's got a partial negative charge there, partial positive, partial positive. A lot of hydrogen bonding with water, strong intermolecular forces, cohesion, adhesion. So let's see. Cohesion is it bonds to itself, so it cooperates. So it's a bunch of hydrogen bonding with water. We can draw tons of those if you want to, but it's not really, we've already done that. So water is a good solvent for that reason. Yeah, okay. And we've done all of this too, I think, before. Water is really good at dissolving soluble ionic and polar covalent compounds. So an example of a nice polar covalent compound would be glucose. But actually water will dissolve anything from those first 3 examples. So basic idea behind why water is so good. Also, it's cheap, it's plentiful, and it is safe. And I think, and the solvation sphere, remember that? So lots of different things we could put there. Probably the easiest thing to do is, even from coordination chemistry, If you have cobalt 2+, it gets surrounded by waters. Remember that? That's what's called a solvation sphere. It's not really the best example, I suppose, because those are really complex ions. But so water will surround an ion or a polar molecule almost like a blanket over glucose, and then that's how it dissolves in water. That's what's happening on a molecular level. Excellent. Okay, take a deep breath. A lot of definitions here at the front end until we get to calculations. Don't need that one. Okay, in a nutshell, strong means it dissolves completely, or in some cases dissociates completely. Weak means it doesn't dissolve very much, or it doesn't dissociate very much. That's what the words strong and weak mean. Right out of the gate, strong and weak have nothing to do with concentration. So maybe I can make that note here. It has nothing to do with concentration. Again, it's just definitions, not too worried about these right now. We'll apply all of these later. I will write down some examples of all of these on the next slide, I think, if I left a slide blank for that. If not, we'll do it in class, because we always have that option. Okay, there's a definition of electrolyte. It conducts electricity. I'll give you some examples of that. And you have strong and weak electrolytes. Okay, fine. If it's an ionic compound, then it dissolves in water. Well, you have a bunch of ions. So you might, that conducts electricity. That's a strong electrolyte. If it dissolves in water, by definition, it conducts electricity. Okay. Well, if it doesn't dissolve, in other words, if it stays as a precipitate, that's not going to conduct electricity. And polar covalent compounds do conduct a little bit of electricity. That's why sugar water will conduct a little bit of electricity, not very well, but that's why it's a weak electrolyte. Okay, fine. Well, okay. It conducts electricity, it doesn't conduct, it conducts a little bit, or it doesn't at all. So it'd be a non-electrolyte, where the conductivity of the solution doesn't change at all. Electrolytes are just a pretty common word, especially in engineering and in exercise science and biology. Not one we use in chemistry a whole lot, but it ties into what we're doing. And what we are going to talk about are acids and bases. And for this particular part of the unit, I'm going to skip the notes that I originally had. Maybe I'll add these in class, but this video's, as many of them, gets a little bit too long. So, acids and bases. And we will learn that there are different definitions for acids and bases. For right now, an acid is H+. A base is something that produces hydroxide or OH-. So if you have an acid that gives you a lot of H+, that's a strong acid. If you have an acid that only gives you a little bit because it doesn't dissociate very much, that's a weak acid. Same for hydroxide. Strong base would give you lots of OH- because it dissociates completely or reacts completely. Or if it's a weak base, it does not give you very much. So the words strong and weak apply to electrolytes, they apply to acids and bases, and we will cycle back with those definitions later. I want to get to some calculations, just a couple to get us started. Oh, there we go. That's just what I said. I got ahead of myself. This is like a real lecture. I do this all the time. Okay, and finally, I left myself some space there, but I'm not gonna do any examples. I'll save that for class. All right, back to concentration, using our 3 solutions as case studies. Different ways of measuring concentration. Let's just get down the definitions, and then we'll do a couple calculations, and we will call it a video. And again, this is where we will end for the first exam. This one, fortunately, you already know. Molarity. That is our most common unit. Molarity is moles of solute per liter. So you have to make a volume and convert to liters. Total solution. That is so important. Total solution. Contrast that with something that sounds the same and the numerator is the same, but the denominator is different. The denominator is kilogram of solvent. Okay, why do we do that? I might as well give away why we do this. You can make a note of this if you want to. Molarity is temperature dependent. Why? Well, a liter is a volume. If you heat it up, what occupies a liter is going to be bigger if you have a container. So sometimes we don't care about temperature dependence of concentration, so molarity is fine, but molality is temperature independent. That's why we use it. Mass doesn't change with temperature. Volume changes with temperature. So there you go. That's the reason we do this. The numerator is the same. The denominator is different. Molarity is total solution. Molality, lowercase m, script m, is kilograms just of the solvent. You see why I'm making that point over and over again. Mole fraction is exactly what it is. It's the fraction of the moles of solute divided by the total moles in the solution. We don't make it a percentage though. We leave it as a fraction, so we don't multiply by 100. But it is exactly what all fractions are. You have a part, what fraction is it of the whole? Just like a percentage without multiplying by 100. And then these last two we already did. All right, I think we're ready to go. 1, 2, and 3 are in boldface because those are the most common ones that we're going to do. 4 and 5, mass percent and volume percent, are not in boldface. I already did those for you, and those just aren't as common. So let's see where we are, and we want to do some sample calculations with the data that you have. I'm just going to do a few of these. Oh, whoops, I forgot about this one. Part per million is another common one, and part per million, we may use this from time to time. Sometimes in the lab we do. It's the milligrams of solvent per liter of total solution. So it's kind of like a mass to volume percent, but you're not multiplying by a percentage. But that's what part per million is. And that's the end of the material for exam 1. But let's maybe do some sample calculations. I forget exactly how I left this here. Hopefully I left a blank slide. If not, and we have to cash out on this video, that's okay.